Welcome back to our session. We're still talking about the energy changes that actually take place in a chemical reaction or in a chemical change. We've also come to a point where we understand that there is a lot of energy involvement in as far as a chemical reaction is concerned, because we are saying that for us to form new substances in a chemical change, energy must be absorbed, by the reacting particles to actually break down, the bonds that exist between the reactants. But on the other hand, while we form new substances, new bonds are forged or formed. As that happens, energy is actually released. So there's two sides to it. Actually, there's energy absorption for bond breaking and energy release for bond formation when we form new substances. So in terms of our mind map, we know something about the bond energy in as far as energy absorption or energy release. So for now, we'll focus our attention on the energy profiles and how energy then is involved in as far as a chemical reaction is concerned. Right. So what we know is that bond energy, is measured in kilojoules per mole. So this is the SI unit of bond energy. Okay, so the change in energy during a chemical reaction is due to bond breaking and bond formation. So we say these two happen subsequent to each other. For us to form new substances, bonds must be broken. So in bond breaking, there is absorption of energy. Okay, so energy is absorbed. Okay, so there is energy absorption. Okay, while during bond formation, there is energy release. So the release of energy is actually coupled to the formation of new bonds. So there is a change in energy in a reaction when reactants are converted to products. So this is what we will talk about in terms of the reaction. Right. Okay. So the change in energy is referred to as the heat of reaction. So what do we mean when we talk about the heat of reaction? We talk about the energy change that takes place in a chemical reaction. So in other words, what we're simply trying to say is that there is a comparison that we need to put in place in as far as amount of energy absorbed when existing bonds were broken versus the amount of energy that was released when new bonds were formed. And when we form new bonds, we're saying that's when we get the products or the new substances, as we would refer to it. So as a result, the comparison between how much is absorbed versus how much is released gives us what we would think of in terms of the heat of reaction. Right. So heat, think of heat in terms of energy. Right. Okay. So the heat of reaction is a measure of the enthalpy change. So there's what we call the enthalpy change, which is actually the heat of reaction. So when we talk about heat of reaction of a chemical change, we're actually talking about the enthalpy change. Right. Okay. So what is enthalpy? Enthalpy is actually the total energy that reactants and products possess when a chemical change does take place. So when we talk about enthalpy, the symbol for enthalpy is actually capital letter H, so which actually has to do with the heat, right? So if we talk about the change in enthalpy of a reaction, so the change in enthalpy, which is our delta H, that's also, so delta suggests change, okay? So enthalpy change is the heat of reaction. So we can refer to enthalpy change as the heat of the reaction. We're still talking about the same thing, which is actually the amount of energy transferred during a chemical reaction. The word transfer is very, very important because in as far as the law of conservation of energy is concerned, we would recall that the amount of energy in any closed system remains constant. What does it mean? Energy cannot be created or destroyed, but can be, transformed from one form of energy to the other. So in any closed system, the amount of energy remains the same. We don't create energy in a chemical reaction or after the chemical reaction, but we can only convert energy from one form to the other. Right. So when we talk about the change in enthalpy, which is the heat of reaction, so when we refer to heat of reaction, we're actually talking about delta H. Okay, so this is our heat of reaction. Right. So the SI unit again of enthalpy change or change in enthalpy is kilojoule per mole. And when we talk about a mole of a substance, remember we are talking about the amount of matter, the SI unit of quantity of matter. Why? Because a mole of any substance actually contains the same number of particles. Now we know that energy is measured in joules, but what do we mean when we talk about a kilojoule? Right, because 1 kilojoule of energy is equals to 1,000 joules, okay? 1,000 joules of energy, okay? So if we say, for argument's sake, we say it's 200 kilojoules, it's actually the same as, if we talk about 200 kilojoules, for argument's sake, we are talking about 200,000 joules of energy. So if we say 200 kilojoules per mole, for argument's sake, we say 200 kilojoules per mole of substance. We are saying that the amount of energy involved is 200, okay, 1,000 joules per mole of a substance, okay, because this is the amount of sample of substance that we have, because it contains the same number of particles. So take note of these SI units. They are very, very important, but we would always talk about the kilojoules, right? Now, if we are to determine, for argument's sake, the enthalpy change of any chemical reaction or chemical change, is the energy of the product or the enthalpy of product. So this is delta, actually delta H, which is the enthalpy change, is equals to enthalpy of products, okay, which is final, okay, enthalpy of products, okay, less the enthalpy of reactants. So any change in science is equals to final minus final. We end up with the product, but initially we started with the reactants. So less the enthalpy of reactants. So this is the change that we talk about. So this is our heat of reaction, okay? So the heat of reaction is the same as the enthalpy change, right? So this is in terms of energy, but remember, the big question is what energy changes happen in a chemical reaction, right? Now let's try and use a practical example to actually determine the enthalpy change using the bond energies. So the bond energy, we understand that it is the amount of energy either absorbed when a bond is broken or amount of energy released when a particular bond is formed. So the bond between two hydrogen atoms in a molecule is, the bond energy is 436 kilojoules per mole. So what does this mean? For us to break this bond per mole of this substance, we need 436,000 joules of energy. Similarly, when the same bond is formed, this is the same amount of energy that is actually released, okay? So there is a balanced equation of reaction, very simple reaction, which involves the formation of water molecules from simple elements, hydrogen and oxygen. So what do we know? We know that hydrogen, it's a diatomic molecule of an element, okay? So if we balance this equation, we'll have 2 moles of hydrogen. This is the simplest ratio in which they react, okay? Then we've got a mole of oxygen, okay, to give us 2 of water, okay? Right, we have something like this, right? This is the as we would represent it, okay? So if I've used models there, so this is the same as that, okay? And then this is O2, okay? So you can either move in between the molecules, the models, or the chemical formula. Now, if you look at this balanced equation and we are to determine the amount of energy that was absorbed, okay, to break these bonds. So enthalpy of the reactive products, bond breaking, so the sum of energy, okay, sum of energy for bond breaking, okay, how much energy was absorbed during bond breaking? We are saying it's 2 multiplied by those of hydrogen, which is 436 kilojoules per mole plus 1 of oxygen, which is one of that, which is 495. Okay, so to break this, we need 495 kilojoules per mole of this substance. Okay, so what does this give us? If we go to our calculator, okay, what do we have? We've got 2 multiplied by 436, okay, plus 495. Okay, this gives us 1367. Okay, so this is 1367. Okay, kilojoules per mole. Okay, right, and then the sum of energy for bond formation. Okay, this is the amount of energy actually that is released, right, is equals to, there is 2. Okay, per molecule of water, there's actually 2 of these. So if we draw a molecule of water, this is what is happening. Okay, that's a molecule of water. Okay, now how many of the oxygen to hydrogen bonds do we have? There's 2 of them, and then there's 2 moles. So it's going to be 2 multiplied by 2 times, that's 463. 463 kilojoules per mole. So if we also do that calculation, what do we have? We have 2 times 2 times 463. Okay, this gives us 1852. Okay, so that's 1852 joules. Okay, kilojoules per mole. Right? So this is the amount of energy that is released when that is actually formed. So we can talk about the enthalpy change in terms of that, in terms of the amount of energy absorbed for bond breaking. And you realize that the energy that was absorbed is actually less than the energy that was released. So in this chemical change, more energy is actually released than absorbed. So the net change in energy is that ultimately in this chemical reaction, energy is actually released, right? Okay, so if we are to actually summarize that, we would say that the enthalpy change of this reaction is equals to 1367, okay, minus amount of energy that was released when bonds were formed, which is 1852, right? So if we to evaluate that, we would then say 1367, okay, 1367 minus, okay, 1852, okay. So the value is negative 485, okay. So this is enthalpy change is equals to negative 485 kilojoules per mole. All right, so this negative value, what exactly does it tell us? Okay, now let's go back again and rewind. We are saying that for any chemical change, there is energy absorbed to break existing bond. At the same time, after that, when we form new bonds or new substances, energy is released. So in any chemical reaction, energy is either absorbed or released. Okay, now by comparison, in this type of a chemical change, more was released than absorbed. As a result, the net energy change is that in this example, energy is actually released, but it doesn't necessarily mean that there was no energy absorption. So in a nutshell, what we're simply saying is that the comparison between the amount of energy absorbed to break the existing bond is less than the amount of energy that is actually released when these new bonds are formed. So that's the main idea. So the enthalpy change, we can use it to determine the enthalpy change by using the amount of energy absorbed versus the amount of energy released. So the net, so in total, energy is actually released in this chemical change. Right, so you can use a lot of examples, but we wouldn't have been able to quantify it had we not been given the bond energies. So in this chemical change, we are saying that the heat of this reaction is minus 485 kilojoules. So the negative suggests that more energy is actually released than absorbed. Okay, that's it for now. We shall take a short break. See you after the break.